Let's talk now about disks. So let's look at the hardware of a disk. We have basically a sequence of circular platters. So these circular platters are broken up into tracks, and each track is broken up into sectors, and so on. These platters are stacked on top of each other with space in the middle. And above each platter is a physical head. So if we've got 4 platters, we've got 4 heads on top. Or in this case, we have 3. These heads actually float like on a Bernoulli cushion of air on top of the head. So they're very close so that they can easily read the magnetic variations on this platter. Unfortunately, they're also so close that if you get cigarette smoke or a human hair or something, that is too big and you'll actually crash this head. That is, it'll hit the platter, which is not a good thing. One thing to know about these sectors, so these sectors are not even angles. So we have more sectors on the outer tracks than we do on the inner tracks. And the reason for that is just there's more magnetic media there. There's more area on the outer tracks than the inner tracks. When we look at a particular track across all of the platters, that ends up with what's called a cylinder. So conceptually, we have these varying tracks of different radii. To uniquely identify a single sector here, we need to know the cylinder, which is the same as the track, the head, and then within that, the sector. When we're trying to actually access a particular location, so let's say we had this cylinder, head, and sector when we get to one of those, how do we actually do that? Well, here's what we do when we want to read and write. Okay, so to read or write, the first thing we do is we need to move the head to the appropriate cylinder or track. So we need to seek to the correct track. Okay? That is where we get seek time. So we've got to actually physically accelerate this, move it, and then decelerate it. Okay? Can be take substantial time. The second thing we need to do, right, once we get to the right track, if we're lucky, the sector happens to be right under the head. If we're unlucky, we just missed it, and we have to wait an entire rotation. On average, we have to wait half a rotation for the sector of interest to come under the head. So we need to rotational latency, which is basically wait for the sector to rotate under the head. And then finally, we've got some actual transfer time. What is this transfer time dependent on? Well, it's dependent on, for example, how long the sector is. That is, how much of an angle it subtends, right? Because that will tell us how much of a rotation we need, what fraction of a rotation. So it may be quicker to read from an outer sector on an outer track than an inner one. And also, if we have a drive that has particularly high density of media so that the sectors are narrower, that could decrease our transfer time. But these are the 3 elements of cost. We have seek time, rotation time, and then we have the transfer time. Okay, always keep those in mind. We have this abstraction of a disk, where the abstraction is we have blocks or sectors from 0 to n minus 1. And then we have the reality. And the reality is we have cylinder, head, and sector. So somewhere we need to do a mapping here. And the question is, where does that mapping come from? That used to be the purview of the operating system, the device driver, the software for this, the drive. So when you installed a drive, you would note how many platters there were, that is how many heads, how many cylinders, sectors, and so on. And then this mapping was done by the operating system. As time went on, that responsibility has been subsumed by the electronics associated with the disk drive. That is, the disk drive controller has this mapping. There are some desiderata about this mapping, so some desired elements. One important desired element is that we have some sense of spatial reference. That is, as we're iterating through the abstract block numbers or sector numbers from 0 to n-1, that these are near each other, that k and k plus 1 are always near each other. So how is that done? Well, we have, to begin with, all of the sectors in a certain cylinder are adjacent to one another. So here we might have, let's say, the inner cylinder, the next cylinder, the next cylinder, the next cylinder, all the way to the last cylinder. So that's good, because that means as we're going from, let's say, 0 to k, where those are all sectors in the same cylinder, that we have no seek time at all. And as we go from now k to k plus 1, and we need to go to the next cylinder, that the seek time is still short, because we don't have to go all the way across the disk. We're just going a little bit. Okay, so we have a little bump there as we go from k to k plus 1, but it's not a huge amount. The second thing we want to make sure of is that we reduce the rotational latency. So it certainly wouldn't be very good if we went from j to j plus 1, let's say. Okay, so we got j plus 1, and here we have a particular platter, and we have a particular track, and here's j. All right. We wouldn't want j plus 1 to be way over here on the other side of the disk, because then after we read j, we'd have to read half a rotation, get to j plus 1. Or what's worse, we wouldn't want to put j plus 1 just past, okay, so that we read j and we have to do an almost another rotation to get to j plus 1. So where do we want j plus 1? Well, you might say you want j plus 1 right next to j, right? So as soon as you read j plus 1 is available. But what if, after we've read j, there's some amount of processing that the disk drive controller needs to do, such that we just missed the beginning of j plus 1? Now, this is the worst possible place for j plus 1 to be, because we've got to wait an entire revolution. So instead, it's up to the disk drive controller to decide when it's finished reading j, where will the head be, and that's where j plus 1 should be. It may be the next adjacent one. It may skip one and be one after that. But that's part of the mapping and how that works. We also have to consider errors. Disks are not perfect. Okay, they can go bad. We can get occasional errors. And so therefore, we use error correcting codes. Right? A simple error detection code would be parity. Right? You've got a collection of bits. You add one more bit, and you set its value such that the XOR of all these is 0. Then if any bit changes, you can tell, because now the XOR is 1. So it's a simple case. You can make more complicated codes such that take more bits and can not only know that an error occurred, but actually correct it. So those are what are called soft errors, where the error correcting code fixed the error. So what happens is that the disk drive basically saves inside each sector. Each sector is a little bigger than it would otherwise be to support the error correcting bits. And then when you read a sector, the disk drive controller can report, hey, here are the bits, they are correct, but just note that I had an error that I had to fix. It can also report a hard error. And that is that the error correcting code detected an error, but couldn't fix it. Do you even want the contents of what it read, knowing that some bits are wrong? It depends. If you got an executable file, then you probably don't need those bits, because you're not going to run that executable file if you can't read it bit for bit from what was stored there, because you want all the exact instructions, you want all the exact globals, everything else. On the other hand, let's say you're reading a, not an MP3, but let's say a dump of a audio CD. Okay, so where we have the uncompressed bits, where the bits are representing what, 44,000 samples a second of the a level, right, a 16-bit level. And so if we were missing one bit there, who cares? Probably even if we're missing several bits, who cares? But we're better off having the sector with, even if there are some bits that are wrong in it, than completely missing the sector. The hard drive controller can take care of dealing with some errors. So it can do sector slipping. So if we initially format the drive, it'll basically have extra sectors that it will save. And as it's doing this mapping from 0 to n-1 to the actual sectors here, it can move some if necessary, skipping over what it finds are bad sectors when it first formats the drive. By the way, these error correcting codes are some of the reason why you never get as much capacity in a hard drive as you think you're paying for. So when a 4 terabyte drive is advertised, that's like all of the bits that are on here, ignoring the fact that many of them are used for error correction, and also ignoring the fact that some of the sectors are going to be reserved for sector slipping or sector sparing. So what are you going to do with the information you got a hard error? You're going to know you have a problem. You need to get a new hard drive. Hopefully you had RAID or some other spare hard drives that were enable you to maybe have a copy of this that was kept live, and you can swap it out and put in a new one. Or you're just going to have to bite the bullet and realize that you've lost that file, at least this sector of that file. Soft errors are an indication that something's going wrong. One soft error in a blue moon, not a problem. If you continue to get soft errors on a hard drive, or certainly if you get soft errors in the same sector, that's telling you that's going bad, and you would be wise to at least copy that file to somewhere else. You have your operating system remap that sector so it no longer uses it, or perhaps your hard drive controller will do that for you. Let's look at the specs for a couple of different hard drives. So these are some I looked up a few years ago. This was a Western Digital Velociraptor. This was a Seagate desktop machine. This one was 1 terabyte. The other was 4 terabytes. Rotational speed, 10,000 RPM. This one only 5,300 RPM. Average rotational latency. This was advertised at 3 milliseconds. This is fairly easy to compute, right? If we look at the rotational latency, is really how much time does it take for half a revolution. So let's convert revolutions per minute. So 10,000 RPM. Let's say revs per minute. Let's actually swap that over because we want to get time per revolution. So let's say we have actually 1 minute with 10,000 revolutions. And then let's convert that to seconds. And let's convert it to milliseconds while we're at it. So let's say we just cancel 1,000, 1,000, 66. So this just equals 6 milliseconds per revolution. How did we get 3? Because the average is a half. So that makes perfect sense. What doesn't make perfect sense is the advertised average rotational latency for disk number 2. Okay, unless they've done some magic where they can have on average less than a half a rotation, and they haven't, this should really be a number closer to like 5.5 or 6, right? Slightly less than half of this. So I don't believe this 4 milliseconds. And then we get an average access time of 6.8 milliseconds. So what's added in here? Basically, we've got the seek time plus the rotational latency. So that says we're seeking at about 3.8 milliseconds. This number 17 milliseconds. What the heck is going on here? Well, maybe they use an underpowered controller to move the heads? Not likely. What's likely is that this is actually physically a larger disk. So this is probably a 3.5 and this is a 5.25. So that means there's physically more space that has to move for that head to get from one end to the other end. So it takes longer. And then if we look at the sustained transfer, this is around 164 megabytes per second, where this one is 132. And they both have a buffer of 64 megabytes. Which is a better drive? It depends on what you want. This certainly has a lower cost per byte. But if you are, I don't know, doing some machine learning problem where the sustained transfer matters a lot and where you are moving around a lot and might have a lot of seeks, the average access time 3 times less almost, might really make this worthwhile. The buffer is used for what? The buffer is used basically to do several things. It will cache requested reads and writes. That's one thing that will happen. So if you do, let's say, a read of a block and then ask for the read of a block again, that may still be in the buffer, and so that's going to quite a bit speed up the time. You might ask about this cache of reads and writes. So there are 2 types of write caches, right? We have a write-through cache where it goes into the cache, but also goes to its main location, in this case onto disk. And only when it's complete onto disk and in the cache does it return and signal that it's complete. Another option that some disk drive controllers have done is once the block has been accepted by the disk drive controller and put in the cache, it will report back to the CPU that in fact the write has completed, even though it's not on disk. How is that safe? It's not. It is really important that if we were to lose power, for example, that it would still end up on disk. These disk drive controllers actually provide that mechanism. How is it, you say, I can have in RAM, basically on this disk drive controller, a block, I remove power, and yet it'll get to the hard drive? And the answer is there must be some additional power available. So maybe it's a supercapacitor or a battery. What is actually used is the energy that is there in this spinning disk. So it's calculated that there's enough energy in this spinning disk that it can siphon some of it off and use that to actually write this information in the write cache that's not present on the disk to the disk. Presumably, it doesn't have enough time to go ahead and seek to the right location. So my guess is it puts it in some special location. And then when you boot back up again, when it gets power again, it will go ahead and read that, find out where it's supposed to go, and go put it where it's supposed to go. But I thought that's a very clever approach.